There we go. What?
Is that RNA structure behind you?
DNA.
Oh.
Double stranded. You need to take bio next year.
No, she does not. No, she does not.
Learn something.
No.
That's where the big boys go to swim. Right, Luke?
Yeah. It wasn't that bad. It's just.
All right. So if you are absent, or if you're out on Thursday and Friday, you need to make sure you go on Schoology. I think I've just got a few notes and then a video on Thursday, and then on Friday. What's on Friday? I think there were a few math quizzes, and then hopefully Monday we're back on the saddle, and I get everybody back, and I wanted to do an outside activity, hopefully, and then get kind of back to normal. The test for Unit 6 should be on January the 19th. If you have a calendar, then I would make sure you put that on there to know when to prepare. Ma'am.
Who made those?
My daughter.
That is beautiful.
She's working in oil pastels, I think, and she's laminating all of it with tape for reasons I don't know, understand.
That's so cute. I love that's inventive.
It should last for a while. Anyway, you guys should be all the way down to part F on nuclear power. We did part A through E before the break. And something new for this this semester that I would normally do, but I hadn't been doing because of all the COVID stuff and how scattered we've been. I will be checking notes after each unit from now on this semester. So that means you need to either have printed off and filled in the things that you're supposed to talk about and discuss, or write them out by hand, and so they should be numbered and easy for me to check and easy for you to fill in everything. Unit 6 notes has already got most of the stuff filled in for you. It's usually just kind of a fill in a blank at the end or a short discussion every few parts, so it shouldn't be that difficult. But I will check these for completion, and so make sure you have those done by the test day, because I will ask you to turn those in, and so I can check those and make sure you have everything. That should be an easy grade for you if you're following along and doing what you're supposed to. So, today's discussion's on nuclear energy. Anybody have any other questions? Hopefully everything got sorted out. I know some people were trying to do some Schoology things over the break. I don't think any of you guys were.
It was gone.
Schoology, some genius either downtown or at Schoology inactivated all members over the break, and which meant nobody could see Schoology, and if you needed to make something up, that was problematic. And up until about yesterday, nobody figured that out or understood why. I mean, I still don't understand why, but nobody really figured out what was going on. I just got emails like, hey, I can't get on Schoology, and I'm like, I don't know what you're talking about. So it should be back up now, and hopefully you 3 people at home that are watching this have checked and making sure you're doing your assignments. So we're down to part number 21. Nuclear power is generated through what? What type of nuclear reactions do we have? I've found out from my first 2 classes that they have no knowledge of nuclear energy or reactions whatsoever. What are the 2 types of nuclear reactions?
Radioactive.
Fusion and fission. You need to know these, okay? Fusion, fission.
Is that what goes in the active fluid?
Sure. Well, which one do we use for nuclear power? Because we only use one of these for nuclear power. Fission, good. So, fusion, we'll go with it first since it's the easier one for me to remember. Fusion means to what?
Fuse together.
Put together. So this is where atoms, where do we see a fusion reaction every day?
Like touching things.
You have a nuclear reaction when you touch something?
Power? Like what?
You see them make nuclear power every day? Now, we do have nuclear power plants in Alabama. We have 2. We have one up. It's called Browns Ferry. It's between Florence and Huntsville. and then there's one down toward Dothan. So we do have 2 nuclear power plants in the state, but I don't think you see those. Where do we see a nuclear, and that's even not a fusion reaction anyway. Where do we see a nuclear fusion reaction every day? I don't know how many brain cells y'all killed while we were out.
Your TV?
Your phone has a nuclear reaction? Your TV has a nuclear reaction?
Okay, I'm thinking of like maybe.
Layla, I'm worried about you. The sun, yes. So every day, the sun, all day, every day, is undergoing nuclear reactions. So you have hydrogen atoms that are slamming together, and they're fusing into 2 hydrogens make a
Hydrogen gas. 2 hydrogens make up a fusion.
Dihydrogen.
helium. Good. So 2 hydrogens slam together, and some energy is released, and they make a helium atom. Good. So, and that happens, and it releases a ton of energy, and that's where those magic rays of sunshine comes from. Now, we don't use nuclear fusion reactions on Earth for energy purposes. Why?
Wouldn't it like explode everything and everyone?
It would be pretty bad, yes. Your book, in fact, I'm going to skip over here. I forgot to read this to your comrades. If you skip over to 330 something, 336. Nuclear fusion. Unfortunately, this is on page 336 on the middle on the right side. Unfortunately, creating fusion on Earth requires a reactor that will heat material to temperatures 10 times those on the core of the sun. Now, I want to say the surface of the sun's about 10,000 degrees or something like that. I think the core's maybe like 1 million or 10 million. It's like a ridiculous amount. So that's pretty problematic when you're trying to capture that energy and use it for something. It says these temperatures make containment extremely difficult. Thus far, most promising techniques have involved suspending superhot material in a magnetic field, but that requires more energy than the actual energy that they get out of the reaction. So I've read about a couple of these where they've got these small little mini nuclear fusion reactors and they're trying to do this. But they're still a long ways from any kind of promising development and using. I mean, it's a lot of energy, and we've got a lot of hydrogen. I mean, you take water and split it, and you make hydrogen gas. We did that in the DNA gel electrophoresis lab. You just add a little electricity to water, and you split it. So it's pretty easy to get hydrogen, and I don't know how hard it is to bump them together to get this reaction to take place. The hard part is, what do you do with all that energy? And how do you contain it and put it into some useful form? So that's our big issue with nuclear fusion. Okay, so nuclear power on 21 is generated through a fission reaction where atoms of uranium-235, which are stored in fuel rods, are split. This is shown on page 332. At the top of 332, you can see this reaction. And let's talk a little bit about radioactive. What does that term mean, radioactive?
Please stop. Please. Please.
It means it's like emitting like
It means the atoms are what?
unstable.
Unstable. Good.
They're active radiable.
So radioactive meaning the atoms are unstable, and I'll give you an example. So I don't know that we did this, Luke, in bio because bio got cut short last year. But normally in bio, we do radioactive dating with carbon. So carbon normally, y'all remember this from chemistry class? Of course not. So carbon normally has 6 protons and 6 neutrons. So for an atomic number of 12. Radioactive carbon is carbon-14. So carbon-13 is an isotope, but carbon-14 is an unstable radioactive isotope. Meaning it's unstable, meaning it wants to lose one of its neutrons. Good, because it's got a bunch and it's unstable, and so it wants to lose them. So uranium-235 is kind of the same way. It's an unstable isotope of uranium, and as it splits, it's releasing these neutrons, and it's getting to a more stable state is essentially what's happening, okay? And so as it does that, it releases energy. We capture that energy and use it for electricity. So on 316 and 317, it talks a little bit. Our nuclear consumption worldwide is about 6%. Some countries, like France, get about 75% of their energy from nuclear. We get around, I want to say about 10 or 15%, somewhere in there nowadays, from nuclear. It says on 319, 9%. I think it's maybe a tad more, but somewhere around that range. Most of it still comes from coal and natural gas, and then probably 15 to 20 from hydroelectric and some renewables. So, one thing I do want to mention, because on Thursday y'all are going to watch a video on this. There's a guy I found doing a TED Talk, and he is some environmental idealist, or he was back in the day, and he wanted to make a push in California for development of renewable energy sources, so wind and solar primarily. And so he pushed for this, and he helped with development and all this work, and eventually he came to the point now where he's doing these TED Talks, and he's basically like, we need to really kind of forget about renewable energy sources, solar and wind, and we need to focus on nuclear because it's a lot better for the environment. And he makes this pretty compelling argument for nuclear as a better option for the environment. And so I'm going to let y'all watch it and see what you think. So the reason for that is wind and solar, there's a couple things. Wind and solar only produce electricity when?
When it's sunny and windy.
Okay. What happens during the nighttime or when it's not windy?
It doesn't work.
It doesn't work. So how do you get electricity?
You
No,
don't.
it's gonna burn.
You still have to burn fossil fuels or do nuclear. Nuclear, when can you get energy from nuclear?
All the time.
Around the clock. I didn't realize this. When we go to like flip on the lights, or let's say in the summertime, we all go and turn on our air conditioner in the middle of the day so we don't burn up in the pits of hell that are Alabama in midsummer. So when we all turn the air conditioner on and it's sucking a bunch of electricity out, there's not a bunch of electricity just stored in a giant battery somewhere. So when we're all turning on our air conditioners and it's pulling electricity, when that demand goes up at the power plant, it's not stored anywhere. So at the power plant, what do they have to do?
Burn.
They have to burn more. So they burn more coal or burn more natural gas, is more so now. So the guy at the power company, he's like, people are using a lot of electricity. You got to turn up the dial on the natural gas and burn more. You can't like turn up the dial on the solar because you're not going to get more out of it. There's only so much you're producing. If it's not used at that time, it's just wasted. The same thing with wind. If you produce a lot of wind energy and it's not used at that time, then you can't store it anywhere. Okay? So either those renewables are not a good option because they're not reliable and produce energy throughout the day when we need them. And so if we invest in like 90% of our energy come from renewables, well, you're going to be out of luck about, half the day or more. Also, solar and wind, after about 30 years, those windmills and those solar panels, what happens? Probably not that long. They run their life cycle. So, and most of them, they're not easily recycled, so you just have to throw them away. Okay? Hurry up, you're distracting people. So, and then solar panels have a ton of like metals, like lead and cadmium and what else they have, like copper and some other stuff that they're used to make, and they're not easily recycled. So you basically just have to throw them away and waste a bunch of stuff, or send them off to some poor African country or somewhere in Southeast Asia and let somebody burn all the plastic off of, and it's really horrible for the environment to get anything back out of it. So environmentally, like, they're problematic for that waste issue that we haven't figured out, okay? And unreliable. So this guy's contention was nuclear is reliable. Nuclear is very reliable. You can do it all throughout the day. It only takes a small amount of nuclear material to make lots of energy for a fairly long period of time. And Really, and if you look down on number 26, there's two big drawbacks to nuclear. What are they? Nuclear is considered a cleaner energy source because it does not produce air pollutants, but it does what?
It's nuclear waste.
You got nuclear waste you got to deal with, and you have the chance of a nuclear disaster. So those are your two big drawbacks. But I would say maybe three of the most important promising things is, one, you've got a reliable, very dense energy source. It doesn't produce air pollutants, and it doesn't release what? CO2. So it doesn't produce any air pollutants like burning coal does, or even a little bit natural gas, but usually not much. And it also doesn't release CO2. So like natural gas is fairly clean burning, not many pollutants. But anytime you burn natural gas, it releases CO2, which contributes to global warming, climate change. But nuclear doesn't do that. The only thing coming out of a nuclear stack is what? You ever seen those big nuclear stacks, maybe on a video or something? They're huge. There's stuff coming, yeah, it's just steam. So that's the only thing coming out. So this guy's contention was like, the nuclear is way better, and there's no air pollutants, there's no CO2 that's going to increase climate change. You've got a lot of energy coming off of it. And if you look on page 335, I'm kind of skipping around here, but y'all figure it out. There's not a lot of nuclear waste that comes from these power plants. And the nuclear waste you have, you can make these big concrete tanks and basically just store it and keep an eye on it. And you're going to have some nuclear waste, but that's a lot less waste than what you have from solar panels and wind and other stuff that's going to take up more room in a landfill. Now, obviously, you have to have a different type of mechanism and you have to keep a closer eye on it, but it's a lot less waste overall. So that's kind of that argument. Now, the other argument for renewables like solar and wind is we can use them, but we've got to have a way of storing that energy. You've got to have a way of, if you're producing lots of solar throughout the day, you've got to be able to store it so that you have some continuous usage. And I watched another TED Talk where an engineer for a company they're developing basically a giant battery, like the size of the gym, and it's using like salts like out of the ocean, so it's not real harmful like lithium for the environment, or cobalt or nickel or some of the other lead, some of the stuff they use for a lot of batteries now. And so they could store that energy in these big batteries, giant batteries during the day, and then they could be used during the night to produce electricity still. Those still aren't online though. And who knows, maybe they figure it out, maybe they don't, I don't know. So we have this kind of conundrum between we're trying to get away from fossil fuels, and everybody has this bad view of nuclear. And after you watch this video today and tomorrow, you're going to have a really bad view of nuclear. But if you can limit, the nuclear meltdowns, which are fairly easy to do. Chernobyl was the big one, and it was really just the Russians being stupid. I think I put that on the internet. So, if we can limit that, then you really have a good, reliable source of energy with very little waste, and that can be basically kept out of the environment in big concrete tanks. So, I'll let you guys decide what you think is best. Number 21, nuclear power is generated through fission reactions. Okay, we talked about that. Fuel rods. Let's look at how nuclear is actually made. Turn to page 333. Nuclear fission releases large amounts of heat, which used to generate steam, which powers so same as your gas and coal. You have these fuel rods, they generate heat, water turns into steam, steam turns fill it up right there and put it in the fridge. Turns a turbine, which turns hooked up to electric generator, which generates electricity, okay? So basically the same thing. As our other power plants, you just have a different source of heat. So where does the energy come from? Well, the uranium is stored on 333 at the top. Uranium is stored in cylindrical tubes called fuel rods. Uranium is processed into pellets, and they're put in the fuel rods, blah, 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 blah. Okay, so they're lowered down in there. That uranium reacts, it gives off energy, and that energy is used to generate the steam, okay? Control rods. Now, this is just more of a FYI. I don't know how much you need to know about this. Control rods help to control the reaction, okay? Can be inserted between fuel rods to absorb excess neutrons, thus slowing or stopping the fission reaction. So it's a way of controlling the reaction to make sure it doesn't get out of hand. So, any questions about the process for a nuclear reactor? Okay, we're all on par with that. 23, radioactivity occurs when the nucleus of a radioactive isotope is unstable. So we talked about that. In this case, we've got uranium-235. There's thorium. There's other stuff that they're working on, but that's the one primarily used. All right, 24. Uranium-235 remains radioactive for a long time. I think its half-life, which we're going to probably calculate tomorrow. The half-life for uranium-235 is something like 700 million years. So this stuff's going to be radioactive for a long time. I mean, it's going to forever, basically. Okay, so it's going to have to be stored for indefinitely, pretty much. Okay. Nuclear power generation it's a fairly clean energy source. It's sustainable over a long period of time. You can do it consistently throughout the day. And we talked about the drawbacks because of the nuclear waste and possible nuclear meltdown. Number 27. If you flip over to page 334 on the right side in the middle, there have been 3 nuclear meltdowns. 2 were pretty significant and 1 not as bad. One in the U.S. is 3 Mile Island. This happened up in Pennsylvania in, did it say, 79. Excuse me. Operators didn't notice the cooling water valve had been closed. Cool water wasn't going to the reactor. The reactor overheated, blah, blah, blah. And they basically just had a meltdown on one of those reactors. Now, they got it stopped and contained it and basically didn't have a huge radioactive leak. But it was close to being really bad because in Pennsylvania, you know, you've got like Pittsburgh and Philadelphia and New York and all these big cities right around there really close. So, they made a movie about it, and it's basically just they weren't doing all the safety checks they needed to. I've actually got the movie, The China Syndrome. We just never have time to watch it, but it's based on that 3 Mile Island incident. The big one's Chernobyl. I'm going to come back to it. Fukushima. Fukushima is the one we talked about that was caused by the tsunami. Tsunami came in, flooded the generators, all that. They couldn't cool them down, and you had a big boom. Let me go over the boom that usually happens in a nuclear meltdown. When you heat up water enough, a lot of times what's going to happen is that water is going to split into oxygen and hydrogen gas, and it's going to go boom. Yes. So you got to be careful there. So yes, there was an explosion at Fukushima. Fortunately, I think the exposure for people was pretty minimal. A lot of that radiation went out to sea, and then they cleared out that area very quickly around that zone. So I think radiation is probably limited on the number of people it affects. And remember, Japan doesn't have a lot of babies. You know, they're not having a lot of kids. So the younger you are, the more radiation affects you because your cells are dividing faster. And the more, if it affects one cell, it's going to affect a bunch of other cells. And y'all are going to see that in the video we watched today. You kind of have this cascade. Whereas if you're older, like me, or even you guys, most of you are stopped growing at this point, it's going to have less of an effect on you because your cells aren't dividing as much. Okay. So, I mean, it can still cause cancer or something, but it's not going to be as bad, especially developmental issues. So, Chernobyl, the sneaky Russians, on April 26, 1986, they had a nuclear meltdown, a bunch of safety violations, removed the control rods, there was no coolant. This total morons, this whole scenario. Caused a big boom. In the video, it says it only released about 3% of the radiation that's there. So the lady in the video makes a good point. She's like, the next Chernobyl is probably Chernobyl, because if there's another massive leak, then it could be as bad or worse than initially what happened. The USSR at that point, they didn't tell anybody that this had happened. They basically went on about their stuff. There were people in neighboring cities that were having parades and stuff. I had an old news video clip of this, but we probably don't have time to watch it. And they didn't tell anybody that this had happened. And so people were outside, they're getting exposed. All this radiation is kind of getting blown over Europe. So eventually in the UK and I think Sweden and France and some of these other countries, they start detecting all this radiation. And you remember how in the earthquake lab, we had to triangulate where the earthquake came from? So basically they did the same thing. They're like, where's this radiation come from? And they went back and they were kind of, and so they put enough pressure on the Russians. They were like, yeah, we had a meltdown. And so eventually they told everybody, but this had happened for 5, 6, 7 days, something like that, before they tell anybody. So people were exposed to massive amounts of radiation. Even over in the UK, they were worried about having to throw away crops because of excess radiation. So you can imagine what it's like in the Ukraine and Belarus in that region. And so you have this massive meltdown and people have to come in and clean it up, and there's a lot of people that die from it. And it was all preventable, but it was just bad stuff that they were doing on their part, okay? And so that's typically kind of where people get scared about nuclear. They think Chernobyl and that could happen here. I just think it's very highly unlikely with the safety protocols we have in place. All right, 28, releases have short and long-term health effects. From the video, here's your assignment for number 28. I want you to record 4 or 5 different significant health effects from the radioactive release of Chernobyl, because some are very significant, and you're going to see that. It's a very sad video. 29, half-lives. We're going to calculate those tomorrow. So those of you at home, you need to make sure you're following along with us, because I think there's one of those half-life questions on the test. And I think, Luke, we didn't even get to half-life last year in bio, did we? So that's going to be pretty new for everyone, okay? Any questions on that section of notes? All right, so nuclear, there are advantages, disadvantages, just like the other. But who knows, maybe in the end, maybe that is our best option. That'll be something you guys kind of have to figure out and think about. So if you want to keep your notes out to 28, you at home should be watching the first half of Chernobyl Heart.